We are at the last part of chapter 2. It has a name. It's called equation of value. They are somehow, easier terms to describe what we will study in this part of the chapter. So basically, think, let's say, student loan. So you are the borrower and I'm the bank. So if you take a student loan of, let's say $10,000 from me, so let's say there are two part of transaction. So let's say here at time 0, you borrow $10,000 from me. So I'm the banker, you are the borrower. So here, I mean, the money goes to your pocket. So let's say according to our contract, you are supposed to pay me back in 2 years. Okay, let's say in one payment. At the end of year 2, you are supposed to pay me back. So let's use solid line. So let's say you need to pay me back $10,500. So how do you understand this business? That means at time 0, this is the present value of not 15, it's $10,500. This is what this chapter is about, equations of value. On the left-hand side, what I have is exactly the present value of this transaction or this loan. On the right-hand side, it is the future value of this loan. And how do I equate them? I need to apply proper discounting or proper accumulation, right? So here I apply discounting, or you can also say the AV of $10,000 is equal to $10,000.50. Of course, the period is 2 years. So when you discount or when you accumulate, you need to make sure the factor is for a 2-year period. Okay. So that's pretty much everything of this section. So inside the box is basically what I meant in the angle of present value. So present value of all money in should be equal to the present value of all money out. So in this long example, at time 0, you will receive $10,000. So you can think that as an inflow to you. At the end of 2 years, you need to pay me $10,500. So that's cash outflow. So the present value of inflow equals the present value of outflow. Or the accumulated value of inflow equals the accumulated value of outflow. So you just need to make sure it is converted to the same time point. So we have been talking that many times. Whenever you need to do some operations, like here we are trying to equate two values, you have to make sure they are at the same time. So here, when we look at the present value is at time 0, when we look at the future value is at time 2. So they must be converted to the same timeline. Of course, things can get more complicated, right? Let's say I don't want you to pay me in one payment. I may want you to pay like every month. So 2 is the 24th month. Right? I want you to pay me over the next 2 years, but I would like to collect something from you every month. Right? Then it's more complicated, right? But it's easy to see that the present value of inflow is still the same, $10,000. Just the outflow is different. It will be the present value of annuity, assuming that you are paying equal payments. If not, it could be something more complicated. Let's say I want you to pay me equal payments of, I don't know, let's say $100, okay, for well, it's a little bit more. So let's say $50 each month, and the remaining at the final month, at the end of 24 months, there will be another lump sum. So it will be an annuity plus a lump sum, right? It can be something even more complicated. So in that case, when you equate the equation, you need to be more careful when you convert different values at different times, all of them to zero. But eventually you are doing the somehow same thing. It's discounting or accumulating to the same point. Okay. Here I put a remark if all of them must be to the same time point. When we convert to time zero, it's present value, but sometimes it's more convenient to do the converting to some middle point or even to the end point. We don't have to do it to time zero. So let's say we have many examples. The first one is 2.12. This is essentially the same as the student loan example I gave you, except that here we have Joe borrowing $4,000 and he will pay back a lump sum. Lump sum means one payment of $4,750. You want to know the interest rate. So that is 2.12 example. So original amount is 4,000, which is the present value at time zero. At the end of 4 years, the payment is 4,750. You discount back by a discounting factor v to the power of 5. Okay, because the payment is a one-time payment at the end of 5 years. Okay, so you solve, you will get v. Once you get v equals 1 over 1 plus I, so you know what is I. Okay, the next one, 2.13. Connie buys an annuity immediate from an insurance company. Connie pays 300,000 in return, receives level payment of X at the end of each year for the next 15 years. The annual effective interest rate is 6%. Calculate the level payment X. So if you want, you can easily draw a table like this. So here you need to pay, or Connie needs to pay 300K for this annuity. After paying this amount, she will receive X. We don't know what X is. At the end of each year for 15 years. So if you want, you can put here. So this is a payment or inflow. So basically what Connie does is to put down some fixed amount, okay? And she will withdraw some level amount of money, X, from this account over the next 15 years. So, you know, it's somehow a financial decision that helps her to make better planning, right? Not overspend in earlier years. So the present value is 300,000. This is X times, this is an annuity immediate for 15 payments or 15 years. I know I is 6%. So we can easily calculate X, right? Because what is my present value for the annuity? 1 plus 0.06 to negative 15 divided by 0.06. So I can easily calculate my value, okay, which is about 30,888 cents, $88 plus 83 cents. The next 2.14, Karen invests some money, $36,370 now. in order to receive 4,500 at the end of each year for n years, with the first payment at time 5 years, using an annual effective interest rate of 7%. So what we don't know is the number of payments or the term of the annuity. Okay, this is obviously a lot more complicated. So let's draw the timeline. She pays at time 0 $36,370 for some annuity. It does not start at time 1. It actually starts at time 5. So it's 1, 2, 3, 4, 5. Okay, at the end of each year for n years. The amount we know is 4,500. So Karen can withdraw 4,500 at time 5 years all the way to, well, I don't know. So here is n. She can receive n equal payments. Now the question is, what is n? By the way, the effective interest rate is 7%. So if we compare to the previous example, here we know the payment, which is 4,500. What we don't know is the number of payments. Right? Previously, we know n is 15, but we don't know x. Now we know x. We want to calculate n. Maybe I can give you another question to, well, x and n are given, but you need to calculate I. Right? You can also do that, but it's a lot more complicated because you have I in both here and here. But anyway, this is the analysis. So I know my present value. There's nothing I need to do. So let's do this as a, shall we do it as a annuity immediate, okay? So if we do this as an annuity immediate, what is your time 0? Right? 4 years is the time 0 for this annuity immediate. In other words, you can think this as a deferred annuity immediate for how many years? 4 years, right? So using the deferred annuity notation, I have deferred by 4 years. I have an annuity immediate for n years. And I have a payment which is 4,500. Okay, this is me using the deferred annuity notation. But deferred annuity is not exactly that hopeful. So I'm going to write this, put it. How do I figure this out? So I know if I look at this as an annuity immediate, the starting time is year 4. Okay, so the end of 4th year. So here at time 4 years. So I will have this annuity immediate, but this is the present value at here, right? At time 4 years. And in order to go back to time 0, I need to discount by 4 years, not 5 years. So that's often well, students get issues here, not 5, because I think this as an annuity immediate. So if I see this as an annuity due, if I see this as an annuity due, my annuity due starts at time 5 years. So when I do this, this is the value here, right? And of course now from time 5 to time 0, I will need to discount by 5 years. So it really depends on how you see or how you value, how you treat the sequence of payments. Mathematically, they are the same. Okay, but of course, from an actuarial point of view, this is totally different, right? So this one, you can think this as an annuity immediate, deferred by 4 years. this is an annuity due deferred for 5 years. So the actuarial meaning, obviously, is different. It's just that the mathematical meaning, it's the same. So from here, we know V, so we can solve. It's just you need to take a logarithm in the end. So I believe you should be able to solve this. Right. So for instance, from here, you can write as divided by 1 plus I. What is I? I is 7%. So it's 1.07 to the fourth. Okay, here is 1 minus 1.07 to negative n divided by 0.07. Right. So you can take all the constants to the other side, and then it becomes 1 minus 1.07 to negative n. Move it around, and then take logarithm. Okay, so you should be able to get the result. N is 20. Okay, please check. Make sure you know how to calculate this. This is somehow more elementary. We have 2.15. David borrows X dollars at time 0 and must repay the loan with payments $45,000 at times 3, 4, 5, and 6. Using an annual effective interest rate, determine the amount of X. So in this case, we don't know the present value, 2.15. So here is X, which is unknown at time 0. We do know when we will need to pay. 3, 4, 5, 6. I mean, of course, you don't need to label everything. Okay, so as long as you know the starting point, you know the end point. So 4 payments to be made. The amount is the same, 45,000. The annual effective interest rate is 9%. So please be careful when you read the question. Sometimes it's effective interest rate, sometimes it's effective rate of discount. So it's either I or D, or maybe sometimes they will give you delta. So be careful of the question. So now we are trying to calculate the present value of this somehow a strange annuity. You can think this as deferred, right? I mean, there are only 4 numbers. So if you, let's call it the stupidest way to solve this is, well, just the discount. For this, I need 3 years. 4 plus 5 plus 6. Think you have a calculator, right? This can be calculated relatively easily, right? So V is 1 divided by 1.09. So can be done in 20 seconds. Of course, we don't want this. We want to analyze. Let's say this is a annuity immediate. So I have 4 payments. Again, 3, 4, 5, 6, there are 4 payments because 3 is included. Okay, so I know the interest rate is 9%. If I see this as an annuity immediate, my initial point is at time 2. Okay, so I discount back by 2 years. Okay, you can also do it as an annuity immediate. Then we need annuity due. Excuse me. Sometimes I misspoke. So here we see this as an annuity immediate. So the starting time will be at point 2. So when I discount back, it's by 2 years. If we see this as an annuity due with double dots, the starting point will be at 3. So when I discount back, the discounting factor is cubic. Okay. So the rest, I believe you can finish. The last question, it's somehow more complicated. Okay, and if you feel okay with example 2.16, you should be ready for the actual SOA questions. So let's study this example together. Marilyn invests $3,500 at time 0 in order to receive payments of $450 at times 1, 2, 3, and so on, with the last payment at time 10 years. Determine the annual effective interest rate that she will earn. For anything that is more complicated or somehow not easy to understand, a timeline will help you. Okay, so again, the default option is the end of the year. So when you see 450 at times 1 year, that means the end of year 1. So here we have the first payment. Here you have second. So in this example, you have 10 payments. The initial investment is 3,500. So it's obvious that the present value is 3,500. I have an annuity immediate. Right. So the question is difficult because solving this equation is difficult. Right. Establish. I mean, it's not difficult to establish this equation. Right. There is no deferral period. It is just a standard annuity immediate. So everything should look straightforward to this step. The difficulty comes from the mathematical part of solving this equation. So obviously, to solve this, we need to write down the, not I. I don't know I. So I always like to use 5%, but here actually I need to calculate this percentage. Okay. So a quick question is, how do I calculate something like this? The truth is you don't. You don't know how to calculate this because this is a non-linear equation. If you have a software like MATLAB, like R, you can easily apply a root function to solve this type of equation. But in general, this is rather difficult to solve. Okay, if you have a quadratic, you can solve. But here, the highest order goes to 10, so it goes to the 10th order. So you wouldn't be able to really solve. No, actually goes to 11th. So you wouldn't be able to solve this equation analytically. Then what can you do? Right. So now let's analyze something. Before we solve this, let me use one more page to study something in general. This is nothing but the present value of annuity immediate. Right? And in the summation terms, it will be V plus V squared plus V cubic goes all the way to V to the nth. So obviously this is, so let's say the n is fixed. Let's fix n. Then a angle n is a function of I. Now I ask you a question. If I goes up, what would the present value change? So if the effective interest rate goes up, how would this present value of annuity immediate respond? Is that clear to you? When the interest rate goes up, the discount factor becomes smaller, which means for the same amount, you need to discount more. So $1 is worth less. So let's say here, so if I is 0%, if there's no interest, it's pretty much the case we are having right now. The interest rate is pretty much 0. Then when you discount, it's $1, it's discounted back to $1, right? When I is 1%, $1 becomes 1 divided by 1.01. It's very close to 1, but less than 1. So if I is 10%, this is 1 divided by 1.1, right? So as you can see, when I becomes bigger and bigger, the present value of $1 becomes smaller and smaller. So in this case, all of them become smaller. So the present value will become smaller. So we know the present value of annuity, it doesn't matter whether it's annuity immediate or annuity due or any perpetuity or anything. As long as you discount, when interest rate goes up, the value goes down. So in this case, we know this part is the increasing function of I, right? So we know this equals 3,500 divided by 450. Of course, you know, you can simplify this a little. Now what you do is you try different values. So this is what we call trial and error. So let's say, what do you want? I always like 5%, so let's try 5%. Okay, so you try 5%. Of course, you can do 450 down here. So you try 5% times 1 minus 1.05 to negative 10 divided by 0.05. I get is 3,474.78. Okay, this is less than what I want. Okay, so I want the right hand side to become bigger. So the present value to become bigger, which means I should think, or I should try a smaller interest rate. Okay, what do we want to try? Let's say we try 4.8. Okay, if you try 4.8, the value you get is $3,508.78. It is bigger than what I want, which means the true interest rate will be less than 5%, but bigger than 4.8%. In most cases, that's enough, because for SOA questions, usually you have 5 options. They will tell you it's between this and that, between this and that. You just need to try, right? So let's say 5 is one of the threshold values. You put 5, it's smaller than what you need. So you know your interest rate should be smaller than 5, and you try the next bar. If it's greater than exactly, then it's in between. So if you want something finer, you can try 4.9%. When you try 4.9%, it's less than 35. So you know it's between 4.8% and 4.9%. You can even go closer, right? But usually that's enough. I will end here for the lecture today.